Hello everyone. So in the previous video, we have discussed the linear regression from the machine learning and data science perspective. And like I mentioned, linear regression is normally used when we need to predict one a variable, especially the continuous variable based on a bunch of independent or continuous and categorical variable. If you don't understand these terms, just ignore that, because in the data set we're gonna see, and then we'll define the continuous and the categorical variables, right? But most keep in mind, mostly we use linear regression to predict a numerical value. If we continuously have a pattern of the value on a straight line, and we just want to predict it, instead of coding the hardcode condition, if we want to use the data to predict, that's where we use the linear regression. So in this video, we're gonna see the demo, like which we have discussed in the last video, and we are going to use PySpark. PySpark is obviously is a combination of the best of both worlds. Like on one side, you are getting the power of the Spark, where you can load the big data into the frame, and you can uh, manipulate, and you can prepare it, and then you can run the PySpark machine learning libraries or the models on that final data set, and extract the outcome. And obviously that outcome that can be presented to the business. So with this introduction, let's jump into our demo environment, and we are going to use DataBricks Community Edition. So one of the best thing with the Community Edition, like I mentioned, always it will provide you all the flexibility to run any kind of testing scenario within the DataBricks. It provides you the capabilities of running the Spark SQL, PySpark, Scala, and R within the cluster environment, and that will really provide you the real experience before you get into any job, and that will boost a lot of confidence of yourself. Once you go for the interview and you interact with the recruiter, uh, considering you have already worked with the real software, you have already worked with the real model. Don't worry about the data set. Data sets are almost the same. We're gonna see in the data engineering side of this journey that almost every data, they later follow the same pattern. Like we store them into the warehouse with data marts, feature mart, and then we extract from there to run the machine learning. And obviously there are exceptions, like we have streaming data, we have the unstructured data. So these are obviously extremes or exceptional cases, which we discuss on case-by-case basis. But obviously organization provide a lot of support to handle these kind of data sets, because they know the level of complexity associated with these data sets. Coming back, we're gonna start simple as usual. So we understand, we get our concept right, and then we can literally run the same model on any size of the data or any kind of the data sets. And by the way, I've already loaded the notebook file and the data sets into Git, into the repo. So if you want, you can download the dataset file and the notebook, and you can run it by yourself. If you don't want to write the whole thing by yourself, if you just want to run it, both things are available. You can use it, right? I'm gonna just put that link in the description of this video. Now coming back in here, so obviously, like you can see the first cell, I'm just going to describe the data set once we load the data, because right now we are within the DataBricks. So once I reach to the point where I can show you the schema, I will explain the data set. But at the moment, we are going to predict the mileage per gallon of a car if we get the attributes of the car, and the user want to predict, okay, how much miles per gallon that car will cover from the distance perspective. So just keep that in mind. These are, like you meant, no, these are the libraries we always use, but there are a couple of additional libraries that we are going to use, which are purely specific to the PySpark. And you can see we have the namespace for PySpark ML, and underneath we have the lin elk, so that is representing linear algebra, because obviously linear regression is sitting under the once in order to prepare the data for our model, we're going to actually convert our data into vector, and vector space sits within the linear algebra. And obviously we have the feature, and we are using one of the assembly from this space, which actually assemble the feature set into the vector, and prepare that vector for our machine learning model. And obviously last but not the least is the actual model itself. Like you can see, we have the regression namespace within the ML namespace, and in the regression space we are calling linear regression. I'm just gonna go through these libraries separately once we go deeper into the PySpark machine learning library video. We're gonna actually open those libraries because they are all available. Their source codes are available. You can literally go dig in, and we're gonna see what kind of functionality is available from this library. So if you don't understand, just remember these three, that we are going to use these three libraries from PySpark, and how they're gonna use it, you're gonna see in the demo. Okay, I've already created a folder into my file store table, and if you don't remember, just visit the video where I actually show you how you can manipulate the file system of the cluster node, and you will see how we can create the new folder, and how we can manage the data sets within those folders. And obviously, let me just show you, because the folder is already there. You can see we have the regression, and regression, under regression we have some table, some files as well. Let me just for your regression, let me run it. Sorry, maybe spell regression. Sorry, I'm missing S. Now it should be all right. So you can see we have automg mpg.csv, the same file I have loaded into the GitHub. And this is a now very common statement which we are running. We are going to now define a variable which contain different attributes for our Spark object to read the data from this file, and load it into our data sets. Sorry, into our data frame. Now we have defined df auto data, and we are going to call the Spark read function to read that CSV and load it with these attributes. Like, we are not going to let Spark to automatically determine the schema. We are not going to we are going to define that the first row contain the header, and obviously the delimiter for CSV is going to be comma. Now you can see the data frame is good. Let me just quickly show you the first 100 rows to sense check the data within the data frame. So you can see we have all these attributes, and we have their corresponding values we can see. And now, if one thing which I want to show you, which is a challenge for us, because we are not letting Spark to define the data types through the infer schema. So now every data type has been converted into a string, which is obviously a problem, because in machine learning, like you always remember, we only use numeric data types, right? We are not going to use any data type which is not going to be numeric, because machine learning won't work on date and vector data type. So for somehow we have different techniques that we use to convert these value. If you want to use them within our machine learning model, we have to first convert into the numerical values, and then we feed it into our machine learning model or algorithm. So now one of the challenge that we have the numerical data, but it is coming with a wrong data type. So we have multiple way we can use, and I'm just gonna show you the easiest way, which I prefer. So what I did, I convert the data set into a view. And by the way, this is considering it's a small data sets with the limited column, but in reality sometimes we have bigger column, bigger tables with where we might have even 100,000, and sometimes even the number of columns are going to be in 100,000. So right, for those we have obviously different techniques to prepare. We apply all this feature engineering before we load the data into our data frame. We can still apply a lot of transformation and do those operation, but that's we will leave it for the later videos once we target some really big data sets that we can run against our machine learning model. For linear regression, I do believe it's enough for us. So I converted it into a view, and I'm just going to now, very first thing I'm going to check that how many records. We have 398 records loaded into my view, and then I'm just going to check is there any duplicate, because these are now part of our exploratory data analysis stage, or our data preparation stage, or feature engineering space, whatever you want to call that stage. Now we are checking our data, whether our data is ready to feed into machine learning model, or we need to do some sort of adjustment. And you will see sometime how much complexity we face while we are preparing the data for our ML models or algorithms. All right. So I'm also checking, do we have any missing value existing into our data sets? So it looks like I don't have any missing values. So you can see all the major attributes are coming. And like I mentioned, because the data set is small, so I can afford these individual cell. But we have even different technique. If you have large cell or large column within our table, we use different technique to check the same thing, to make sure the data set is correct and complete. So far so good, like all the columns are fully populated, there's no duplicate. Now the biggest challenge for us to convert the string values into double, right, or into integer, whatever data type you want to use. I'm using double because I've seen that the data has some numerical values with precision, so I need to make sure they are not going to be rounded one if I use the integer data type. So the statement is very simple. We're going to use the cost function. And if you don't understand these function, please visit my video to see how we are using SQL in Spark, because that's the full wrapper that is available to us through DataBricks, and we can use this wrapper to prepare our data. So you can see a real power of multiple languages, or data engineering and data science. They are both working side by side, to achieving one goal. So I'm converting all the values except let me just let me hide that thing. I'll discuss why I have actually commented this condition, and car is not going, because car is the data set. And let me run it. So you can see the data has been converted successfully. And now what I'm going to do, I'm going to now load this data, because that's the beauty. So once you prepare your data at the SQL level, so now that data is within the temporary view, right? Now we want to load it back into our data frame. So we just need to call this spark.sql function, and we just need to put our query. Whatever the result will be, it will load into the data frame, and then we have the full power of the data frame, which is the core strength of the Spark language. So let me load it, and now I think we are good. Let me just display the transform data set. And I'm going to do one more thing. I'm just going to let me use auto prepare. I don't know, sometimes it didn't use the license, and some it does. So if okay, now it's right. By the way, this, we are using PySpark, and if you know Python, the Spark is sensitive to indentation. Like if you add some additional space within the statement, it's gonna give you the error, because based on the space sequence, it identify the blocks within the statements. Right. So that was the error. Now you can see the data types are correct, and we are ready to use our data set for our machine learning model. By the way, we haven't used the car name, because obviously, like I mentioned, the string values are not going to impact on our model until unless we use the NLP, natural language processing, where the string data is contributing into the machine learning algorithm. But most of the algorithm in the machine learning, which we're gonna initially use, they require the numerical values. All right. So the data types are good, and we have seen the data, and there's a difference between display and show. Show always return the first 1,000 rows, and in some cases it will get the parameter, and based on that parameter it returns the row. Display always return the full data set. So keep in mind that you have to be very careful, because with display, regardless of the the data set, is try to return you the full data set until unless it crashed the notebook, right? So we have to be very careful, because I know it's a small data set, so that's why I'm actually using it. So now let me quickly show you the summary of our data set. So what we are seeing in here, normally we see, especially with the linear regression, if you remember, in the mathematics, like I mentioned, in linear regression, we need to see the mean, because mean is very relevant. And the standard deviation is relevant as well from this test perspective. But let me just talk about the summary. It is providing us the count of all the columns, how many columns, how many records we have in each column, how many values, mean of those values, standard deviation, mean, and max. Obviously, we can, if you want more, like variance or any other additional statistical function, we can call the libraries and we can include those as well. But these are more like by default these functions are available, so we can gain the advantage by just quickly have a sense check. Now, with the linear regression, one of the most important topic is to check the correlation, because remember, in the linear regression, we normally use those independent variable which are highly correlated with our dependent variable, and the dependent variable is the one which we are going to predict. Now, coming back to the discussion of the data set, because now I think that's the time that we can discuss the concept of our data set which we are going to use. So you can see we have the car data set, and even let me come in here. You can see each car, it has its origin, which is obviously controlled by the code, and its model year, and obviously the acceleration, the car weights, obviously it's in kg, and the horsepower of the car, displacement, and the cylinders, and the miles per gallon. So that's the whole. These are all the attributes of the car, and obviously based on these attributes from cylinder all the way to the origin, based on that we are going to predict the mileage per gallon of that car. So for example, if we have an auto company which is recommending the cars to our customer, so whatever car customer is asking, we are just and he is quite conscious about how much mile the car is gonna cover per gallon. So based on the attribute of the car, they can feed in and they can predict that, okay, these are the estimate, or these are the predictive mileage per gallon for your car. So you can see we don't have any algorithm, or we don't have hardcore condition. If the cylinder is this, and displacement is this, and horsepower is this, and weight is range between this, and acceleration is this, and then we put a condition, that is all gone. And that's where machine learning really shines, and that's where the data science is gaining so much popularity, because it doesn't require business to define the rule. It read out the data and then it makes the decision or make the prediction. So that's the most powerful attribute of the machine learning and data science field. And you're gonna see it really in action by yourself now. Okay. So now we have discussed the data set. So obviously we have the one variable, which in this case is miles per gallon, which we want to predict. And then we have all these input variable, which are obviously independent, that we're going to feed to predict that value, right? So obviously we're going to see, is there any relationship between the dependent variable and the independent variable? Because that relationship will help us to include or exclude the variable. Because if there is no relationship, so for example, if car name is not contributing in the MPG of the car, that means it's not going to actually benefit anyway once we feed it into the algorithm, because algorithm needs to use some relationship between these two variables to predict the new value. And how it's going to actually happen, we're going to see even from in the mathematical video, which is going to be after this one, or slowly we're going to actually see in the upcoming cells once we move towards that section. So that relationship can be either two-way. Once, if we are increasing one value, the other value is decreasing, that's the negative relationship. And if we are increasing a value, the other value is increasing as well, that's the positive. The first one we call negative correlation, and the second one we call positive correlation. But both correlation will define the relationship between these two variables. Now, I'm going to show you the relationship between most of the attributes in this data set. So for example, cylinder, we're going to see whether the cylinder and the miles per gallon, do they have any relationship based on our data. Now, if you look at, you're going to see, yeah, we have the data. They are negatively correlated. Like the more cylinder you have, the less mileage per gallon the car gonna do. So you can even judge it by yourself, and you can understand the correctness of this claim, that obviously more cylinder, it's going to actually use less mileage in a gallon. Okay, acceleration, it has a positive correlation. Like more acceleration, it's gonna have the more mileage per gallon. Horsepower, again, it has the negative correlation, because what's gonna do, it's gonna have the negative correlation with miles per gallon. Obviously, the more power horsepower car has, it's gonna cover less mileage within the gallon. And these are the area where you need to even if you have some knowledge of the domain, that will really help you to understand the data. Now, if someone doesn't understand how the car works, or why the horsepower is impacting on the miles per gallon, he might build the algorithm, but obviously that's not going to actually help him or her to fully understand the mechanics, and that's where one of the data science field that you want to master is the domain which you are working. Whatever industry or whatever business you are working in, you need to get the knowledge of the business. So it will help you to input that knowledge while you are investigating these attributes before feeding it into the machine learning model. You can estimate, and you can understand, because obviously if you have better understanding, you can provide a better outcome to the business users. Origin is the correlation is low. You can see the acceleration and origin, their correlation is comparatively low compared to horsepower and cylinder. And let's see model per year. It has again a low correlation, and obviously the weight is going to have high correlation with our miles per gallon. All right. Now the same thing which we have seen on the top, let's draw that in the graphical area, because there's a famous saying: if you cannot draw, you cannot understand the data. Right. So what we are going to do, we are going to first see the relationship between, because the relationship between weight and mileage per gallon is quite high, and they are negatively correlated. So you can see the less weight we have, because on the x-axis we have weight, and on the y-axis, because that's normally the norm, we always keep our predictive variable that we are going to predict is on the y-axis, and all the independent variable which are going to use for prediction, they are always going to be on x-axis. So you can see where the weight is less, we can see the mileage per gallon is high, and as soon as the weight is increasing, you can see the mileage is dropping, and obviously with the 5,000 kg weight, we have really low mileage per gallon. So you can see the same discussion that we have discussed verbally. Now we can literally draw, and we can sense check by ourselves graphically, right? So that's where the whole data science and machine learning field work, where we not only claim the data, we look at the data from the numerical perspective, but we also draw and we'll see the spectrum, right? And that's another thing, where we called it that machine learning and data science help us to identify the patterns, help us to identify the hidden knowledge within the data. So you can see how we are identifying the pattern and how we are building the relationship by just reading the data. So that's which is linked to all that statement that normally claim in the industry. And obviously, yeah, I can run this. I can show you. Let me see why it is not missing. Yeah, I am missing. I'm just going to, because in this outcome, we are unable to so there is, I think there must be some error. Yeah, there is. Let me see. Yeah. So all, I think that's all. Let me see. Unexpected end of parsing. Alrighty. So then. Now there's better. Yeah. Let me just first go in here. So so we have seen the relationship between the dependent and independent variable. In here, a very important concept which we are going to discuss, which is relationship between independent variable. We call it collinearity. So what does it mean, collinearity? Normally we use those variables which are not dependent upon each other. Understand this point very carefully because that impacts on the final outcome of the model. And the reason is obviously we use the independent variable to predict the value. But if these independent variable are depending upon each other, that's gonna impact on the final outcome of the model. So we need to only use, because if the two variables they are highly correlated to each other, we can use one of them because they are not going to impact in any way to the final outcome of our machine learning model result, because we can use both of them, and we can use one of them, we're gonna get almost a similar outcome. And in some cases, using both, they sometimes impact negatively on the outcome. So that's why it is always recommended to use those independent variables which are not depending upon each other. So that's where we need to check the interrelationship between these independent variables, which we are going to use to predict the dependent variable. Which in this case, obviously, we have all these weight, cylinder, and horsepower. All these variable we need to check, are they linked to each other? And unfortunately, in this data set, I'm going to actually show you. Now we have that data of the weight and cylinder. I'm just going to, and it will show you. If you want to, the beauty with the DataBricks, that you can convert your data into the graph on the fly. Like, you don't need to import additional library. Based on the cell output, you can convert that output into the chart. So let me use this scatter chart because we are going to represent in the number. And let me come in here. We are going to use the weight, and we are going to use the cylinder. These are the values, so you can see. And now if I think that should be all right. Yeah, let me apply it. So it is still showing me you can see there are categories. And let me see if I can, how about if I just, cylinder is a series. Okay. I think the representation is not simple. I just want to keep it simple, so that's where I was thinking, because and how about if I just pause our right. Yeah, I think that's a better example. Let's take that one. I will tell you why the other chart was not correct once we discuss the categorical and continuous variable. But right now, just use this example. These two variables are the way. So both variables are independent in our model, but you can see both variables are highly dependent upon each other. Like, you can see there is a very positive correlation between these two, horsepower and weight. Like, you can see the weight is increasing and the horsepower is increasing as well. So these are always non-recommended because they will impact on negatively on the final outcome of the model. Just keep in mind that's there we have one defect that we want to find out how we can resolve it. Well, obviously, this is a simple model, so we are not going to discuss these things in here. We just want to understand the linear regression, but that's some challenges. Sometimes we think, oh, now we develop the machine learning algorithm, the model is in the production. What we gonna do now? These are the improvements we continuously make to improve the prediction or the outcome of our model. We keep investigating these areas to improve, and very slight improvements very slight changes or improvements make big differences in the final outcome, especially in the machine learning and in the data science domain. So again, we're gonna see there's a high correlation between weight and displacement, and obviously cylinder. I've just actually put them in each cell so you can see the correlation, and some of them are very low, like the model year and the displacement. They don't have any good strong correlation. Now, so we check all our data. So the data is almost correct. And once I say almost correct, that means I know there are some interdependence exist in our input data, which is going to use to predict the outcome. But right now we can live with that. And now I'm going to create my vector assembler. What it does, it actually stitch all the features and create one vector, which is going to use to feed into our machine learning model. Because obviously at some later stage we're gonna divide our data set into train and test. So, and we need to feed the data in terms of vectors. How the vectors are work, what kind of structure it is, we're gonna discuss once we look at the feature engineering and the array concept used in the from the linear algebra perspective. So what I'm going to do, so you can see I've just provided the input column information, and I'm only providing those input column which I'm going to use to feed into my model. And I just put that, okay, these model, these input column, they are going to stitch together to create a vector, and I just give them a name called features, right? So that's my feature column, and it's going to contain all the value. And then I'm just going to convert them into the feature set that I'm going to use into my machine learning model. So you can see I'm just calling the transform, and it's going to return me again the data frame, but this time there is a difference. I have all my columns, but beside that, out of all these columns of the data frame, I have a vector column which has been composition of all the input column, which I have actually defined in my vector assembler. And the library name is very descriptive, like it assemble a vector, and vector is it's more like is the sequence of value or array of value that you are going to feed into the machine learning model. Now, obviously, we are ready. Our data set is ready. We are going to now only select the features, because we are not going to individually feed the attribute. We are just going to feed the vector, which we have prepared based on our feature, and we are going to feed the output or a dependent variable to our model, so we can later on predict the dependent variable for unknown data. So you can see I have prepared a data frame based on my two columns. One is feature and the other one is miles per gallon. And now let me display my data set. So you can see we have our data model, and you can see that that's the vector type. So you can see it has converted, the length is 7, and you can see the value is coming as an array or as a sequence of value. If you don't understand array, don't ignore it. We're gonna discuss it at some stage. All right, now let me divide my data set in the random split. And why we do it, we normally we always use some part of the data to train our machine learning algorithm, and then we use unknown data to check the accuracy, that how accurately our machine learning model predict the unseen data. Because if we feed all the data into our machine learning model, then we don't have anything to test it, right? We need to wait until unless the real data comes in, and it might not give us the full accuracy or full picture of the accuracy of our model. That's why we always split the data between training and testing, and we always use trained data to train our model. In this case, In the next video, once we look at the line, we're gonna see how we can get the best fit line of the linear regression. And in order to use that best fit line, we're gonna use the training data. And once that best fit line is gonna be achieved and we have our model ready, we're gonna feed the test data to see the accuracy of the machine learning model. I have introduced another one, which is the validation. After feeding the test data, we get the accuracy. And then if you want to test, some unknown values, which we believe that, okay, this model hasn't been shown. That's why I actually took the 20% as a validation data just to validate, you can, put this value and then see what machine learning model is returning you as a value of miles per gallon, and you can compare because you already have the actual value, so you can compare against the actual value and you can see the differences. And like I mentioned, machine learning model or data engineering, data science model never ever give you 100% a result. They are always close to 100%. Keep in mind there are differences between getting 100% outcome and close to 100% outcome, right? And that's one of the biggest topic of the data science and machine learning area. All right, so I have divided it. Let me just quickly show you the structure. We have the total 171 records in our training set, and we have two columns. We are going to call the linear regression function that we have defined up. Now, like if you remember in my first introduction video, these machine learning model, they are more like a black box. You just need to feed in. These are all the built-in, agreed upon, accurate, and industry standard model that you can use out of the box. You never ever need to think about the efficiency or the accuracy of these model, because enough research in the last 2 decades has been invested to build this model, right? So you can safely put your data and you can get the result with the confidence, yeah, your model is working fine. If there are issue, it's always going to be your data. Remember, if you are feeding a garbage into your machine learning model, you're gonna get the garbage. If you are feeding the best data, you're gonna get the best outcome. And that's where the whole effort and energy has been invested into data preparation and data formation, so we can get the best outcome of our machine learning model. Okay, now we have our model ready. Like I mentioned, that we have the linear regression function which is available, and all we need to pass the output variable or the dependent variable, or excuse me, or the variable that we want to predict, right? And it will create the object for that model for us. And now once we have that object is ready, we just need to call the fit. So most of the machine learning model, they provide you the fit function. What it does, it actually take the parameter as a data set or whatever data you are going to feed from the training perspective, and based on that it actually train the model. That's what it has called as fit. And once that has been done, it returns us the object that we can use to predict the unseen data set, or we normally called test data set. So what we are going to do, like I mentioned, our training data set is ready. We are going to feed the training model. And then our model is ready, and we are going to, especially with the linear regression, we are going to get two important parameters. One is called the coefficient, the other one is called the intercept. If you don't understand the coefficient and intercept, just wait for the next mathematical explanation of the linear algebra regression video, and I'm going to actually show you how the coefficient and intercept actually work in the linear regression. But just for this one, just imagine that we have the straight line which we are trying to calculate. So we can use it. So we can use that equation to predict new value. In order to predict the new value, we need the coefficient of the variable that has been used within that equation. So, for example, if I just for the sake of understanding, if my equation is, let me just take a very simple mx plus c equation, which we have already seen in the introductory video, right? And we discussed it there. Now that m and c, they are going to be the coefficient, because we need this value. If we have this value, so we can predict any value of y given value of x. So that's the whole mathematical explanation on a very high level. Underneath there is lots and lots of going on, but just for yourself, because you are not going to become the mathematician or statistician, so you only need to learn those part of these two fields, which can only help you to drive your model, right? So just imagine these coefficients. So you can, if you can calculate how many coefficients we are getting, 1 2 3 4 5 6 7, that means we are getting the coefficient by each column. So if we actually calculate the column, or calculate the independent variable which we are feeding to our model, so all the coefficients we are going to get are exactly equal to the number of input variables that we are feeding into our model, and in this case number of columns. So if we can count, say 1 2 3 4 5 6 7, so you can see based on that we can understand, okay, these coefficients are more like, you know, the values of each column coefficient in the equation, and based on that, so for example, let me tell you, if we have let's say 7 columns, right? So how it's going to actually happen, if I actually build the equation for 7 columns, y is equal to, and let me just change the convention from, let's say, m0, and it's going to be x0, right? Which is obviously equal to 1. So we are normally, we won't write it, right? Let me just write it. And then we have the m1 x1, and then we have m2 x2, all the way we have mn xn, and then we have intercept, which is c. Now you can see these are all the values which we are getting, and by the way, I started with 0. You can start with subscript 1 to exactly equate the number of the coefficient that you are getting, right? So that's what this model is returning. Also, this model is also returning me another important parameter, which is intercept, which actually, so we, based on these coefficient and intercept combination, if I have all these value now, so once I get the values of these these parameter, now all I need the independent variable value. So for example, if I take the example of my data set, so now if I get a new car, completely unknown, where I want to predict the mileage per gallon. So all I need the value of these 7 columns, and then using that equation, I can predict the value of y, which is equivalent to the MPG, which is miles per gallon. So that's how we will use the machine learning model to predict the value. And remember, again, this value is not going to be accurate all the time. That's why we have the error information, and that's where we minimize the error, and that's where the whole optimization come into the picture. Now coming back, let me just run this. So we have the intercept, which is -16, and now our model is ready. We have already feed the model with our training data set, and now I'm going to actually check the accuracy of my model, because I already considered, remember, we already have the actual value. So what we're going to do, we're first going to actually evaluate the accuracy of our model based on the training data. So we have the evaluate function, which actually use the data set and try to find out the accuracy in terms of the percentage. So for example, out of 10 records, 8 of them are coming exactly equal to your actual value, where the predicted value and the actual values are equal. So that means the accuracy is going to be 80%, because 8 values out of 10 are correct and 2 are incorrect, right? So based on that, we will calculate the accuracy of our model. So if I run it, so I'm going to see the accuracy of my model. Let me just print it. And what is R square? Just ignore it. It's more like a parameter at this stage, which actually tell us the exactly the ratio, the accuracy of the model. And you can see our accuracy is pretty good, like 85.49%. You can convert it into percentage. It is coming in the fraction, right? But that is showing us that it is the 85% accurately predicting the value of the miles per gallon. Now, by the way, once we go into the real world modeling, the percentage normally drops just because of the challenges with the data, and obviously that's where the whole time the data scientists and machine learner engineers they spend to improve the accuracy, and that's the accuracy which we are talking now. So our training data is quite good. What I'm going to do, our model is ready, training data set we have checked, it is 85% accurate, which is a handsome and acceptable accuracy from the business. Now put it into the test. So what we are going to do, we are going to evaluate based on our 20% test data set that we have put it separate, which is completely unknown to my model that I have built in. All right. Now I'm going to check the prediction accuracy. That is even more than 86.4%. So you can see that our model is performing really good. The data set it has used to train, it is performing better than that data set. That it is behaving good for the unknown values. So that's the whole point, of separating the data into train and test. And by the way, you run it multiple times, you're gonna see different, results. Sometimes the training accuracy gonna go up and go down, and sometimes testing accuracy is gonna go up and down. Because it is all depend upon that line. All right, so just for us show you, these are the testing data set, and now we still have our validation data set that we can use to to manually predict the actual value, because right now we are only seeing the accuracy. We are not seeing the actual result, what it is providing as an outcome of the model against the actual value. I'm going to actually put it in a separate video because this video is already quite long. That we'll see if we want to literally feed a row and then see the result and compare it with the actual value, we can still do it, right? So that's going to be a couple of additional cells we're going to actually build on, and then we'll show that data as we're going to show that accuracy as well. I'm just going to keep that validation data frame as it is. I'm not going to actually show you the anyway, I can show you the accuracy. So the prediction accuracy is way better than the prediction accuracy of the above two, which is training and testing, right? And obviously then we can show you the validation data as well, right? So in the after the mathematical explanation, we're going to put a video where we can feed the values and see what our model is predicting from the regression perspective, and then we compare it with the actual value to see whether this ratio is making any sense or not. So that's all about the linear regression, the very first machine learning model we have built from end to end, and we have discussed. There are still a lot of areas that requires lots and lots of explanation. We haven't actually seen the error how the R square is calculating, what is root mean square, and how we can improve the root mean square. All these, efficiency area, optimization area, we haven't discussed it. We're gonna discuss once we have a good grip on the machine learning algorithms or model, and then we have a very strong understanding. So it will help us to implement these improvement or optimization to our model. I do believe this video will be very helpful for you to start your machine learning and data science journey. Please feel free to like the video and put any comments if you have any question. Otherwise, I'm gonna see you in the next video where we're gonna explain the same model from the mathematical perspective. Stay tuned. Thanks for watching.